Hello everyone. So let's take a little break from science and stuff. I'm just going to do advertisement for my beamline. So I'm Arnaud. I'm a beamline scientist at the National Secretary Innovation Center. So this is our facility. So with our two synchrotron, so we have the old one TLS and new one TPS. And so many of you maybe know what a synchrotron is. But for those of you who maybe don't know, it's a big accelerator that we use to produce X-ray to do a lot of different experiments, to do a lot of measurements. So that's how it looks like. So we have an accelerator here, storage agents, and so some beamline. And so I'm a scientist at one of these beamline, which is still under construction. We should be finished soon, which is, I'm here to talk about it. So because in here there's a lot of physics, biology, and maybe a lot of you use synchrotron all the time already. Some of you maybe not. So the TPS ring can do a lot of different experiments. So diffraction, imaging, and spectroscopy mainly, and a lot of different measurements possible. So we use X-ray to use a lot of different things. And so maybe there's people here that could have interest in making measurement of facility. But I'm going to talk only about my beamline, which is TPS 15A, which is this one, which is microcrystalline X-ray diffraction beamline. So our main technique, so I'm sure many of you know X-ray diffraction already. Use a crystal, shoot X-ray at it. We can take this with a detector. We have beautiful diffraction pattern, like this one. And then with the computer, we can recompute the crystal structure of material. So our beamline is focused on small molecule chemistry. So this is the layout of our beamline. Starting with the hard undulator, a lot of optic mass, and we will have two end stations. So one end station is high flux, but the beam, not both standard measurement, and a second beamline, a second end station, sorry, where we will have the microfocus beam. So slightly lower flux, but actually higher brightness. Sorry. We also have a femtosecond laser here that can detect to this beamline to do like super fast, high resolution measurements. So this is our source. So we have an energy range 30. Have like a cryo-undulator long. We generate this energy range, and so we can produce either a multi beam or a pin beam to create two different sizes of beam station. For sample environment, we will have 4 different types of cooling, so just simple nitrogen or helium for people who need to measure very low temperature. So I said that we have 50 lasers, so we can do either just a simple radiation or 10 prong femtosecond measurement. We have also a lot of diamond cell that measure at a very high pressure. And including some stage that we can use at low temperature down to maybe, and also a system to heat to make measurement at high temperature. So with all this strange. Okay. So with all this setting, we can make this kind of arrangement. So we all So some environment, so we can make measurements. So the primary goal is to have like microcrystal which you cannot measure with a lab instruments. So chemical compounds. That's the main goal of our demand. As you can see, you can do a lot of high pressure, but with also basically everything non-ambient, so pressure, temperature, or light irradiation. So still with light irradiation, you can probe at the second. We can do charge density with these two, and finally, can do like crystal mapping, and this is something that I'm very interested about, so I'm going to detail this a little bit. So if you have never seen something, so this is a bending crystal. It's really one crystal that can be bent. And actually this one specifically is so bendable that you can not. It's still a single crystal, but no break, no damage to it. And on a spectrum facility, it's actually possible with a microscope to have like one of these bent crystals and have the beam proof, or not the beam crystal. And can actually, with the diffraction pattern, have a structure. You can see on the edge, or and so, and you can see like the contraction and expansion. So we have like a lot of contraction here, very compressed inside the see this crystal structure. And so we can measure the corresponding deformation position. See basically how each interaction changes. It's compressed. So full crystal structure. Anyway, so that's one of the possibilities, and that's something that I'm really interested about. Anyway, in terms of time scale, so we're still a bit in the construction, but it should be finished very, very soon, and we should start operating. We will have for the first basic test user. Hopefully, if nothing goes wrong at the end of the year, second half of this year, station 1, and then station 2. And for operation, we also have position for attaching positions in the moment. Yeah, and that's it.